In Chapter 6, we're going to extend what we learned in Chapter 5 by looking at some irregular cash flow patterns and annuities, which are those repeated payments such as a house payment or car payment. Then we'll look at effective annual rates to see how compounding within the year really affects the rate that a borrower is paying or that an investor is earning. And finally, we'll look at an amortization table and see how a loan gets paid down to zero over time. Let's start with an irregular cash flow pattern. In this investment project, it will provide you $100 1 year from now and $500 2 years from now. We're going to discount those cash flows at 6% to see what this investment is worth. Those cash flows can just be discounted separately for the appropriate number of years, and then their present values could be added together, and that will give us the total value of the investment, because the value of an investment is the sum of the present values of all the cash flows that the investment will provide. So discounting the $100 cash flow at the 6% required rate of return for 1 year, and discounting the $500 cash flow at the 6% required rate of return for the 2 years will give us the present value of each cash flow individually, as shown, and then the present value of the total investment is the sum of the two, in this case $539.34. Now, one way to think about this value here as being the appropriate value for this investment here is that if you put this amount of money on interest at 6%, which is the rate we used to come up with this value in the first place. So if you invested $539.34 at 6%, that should produce $100 for you 1 year from now and $500 2 years from now. So let's check that out and see if that makes sense, that this is the appropriate amount to pay for this investment. If I invest the $539.34 today at 6%, then in 1 year I will have 6% more cash, which would be $571.70 1 year from now. At that point, the investment was offering me $100. So I should be able to get the $100 out of the investment like I was promised. And once I do that, I would be left with the $471.70, and that's 1 year from now after I take the $100 cash flow out. So then I would invest that at the 6% return that I'm offering, so it would are being offered, so that would grow at 6%. So then in 2 years' time, I would have $500, and that would allow me to take out the second $500 cash flow, and there would be nothing left. So I would be able to pay the $539.34 today for this investment and earn my 6% return on that, because it would grow at 6%. In 1 year I could pull the $100 payment out, reinvest that amount for the 6% return, and that will produce the $500 at the end of year 2. So we always want to think about present value as being an idea of indifference. I'm indifferent between the $539.34 today or $100 1 year from now and $500 2 years from now. So these two future cash flows are worth the same as $539.34 in today's dollars. I just discounted those and added them together and got the $539.34 present value. If I pay this amount today for an investment that gives me those two cash flows in the future, I will earn a 6% return on the amount that I invested today. Now let's talk about annuities. It takes three things to make an annuity: a level, stream of cash flows, which means every cash flow is the same number of dollars. So a level cash flow stream for some fixed or finite period of time, meaning it has an end, and the payments are a constant period apart, such as a payment is made every year, every month, or every week, or something like that. So those three things make an annuity. Same amount of cash flow, fixed or finite period of time, a constant time period apart between all the payments. There are two types of annuities based upon when the payments are made. Ordinary annuities are annuities where the payments come at the end of the period. Annuities due are where the payments come at the beginning. So an example of an ordinary annuity, given the name, it's what you would ordinarily encounter. An example of an ordinary annuity where the payments come at the end would be a house or a car payment, a typical loan arrangement. You borrow the money up front and you don't make a payment immediately upon borrowing the money, otherwise they would just lower the amount you borrow. You don't make the payment immediately upon borrowing the money, you make it one period later, such as if you take out a home mortgage, then you'll make your first payment 1 month after you took that loan out. Now I know they round it to establish the payment to be due on the first of the month typically, but the point is you don't make the payment immediately when the loan started, you make it one period later. If you buy a car, you'll pay a month after you bought the car. Annuities due are still something you would encounter fairly frequently. If you rent an apartment or if a commercial lease on an office building or something like that, you tend to pay up front. You pay your rent at the beginning of the month and then you occupy the apartment or the building for the month after you paid up front. Let's start with the future value of an annuity. In Table A4 of the appendix, you can see future value factors for the annuity. You can also see the formula used to calculate those factors. We're not going to use the formulas. There are examples in the course notes. We'll use the calculator, and at any time you'd like to verify those with the formula, you're welcome to do so. Future value of an annuity is simply the sum of the future values of each of the individual cash flows in that annuity stream. Like the $100 and $500 cash flows on the irregular example, we just discounted them separately and added them up. In an annuity, we would do the same thing. We would just discount all of those cash flows separately and add them together, and that would give us the future value of the annuity. So we say future values are additive. We just add them up, and that gives us the future value of the investment. Here is that factor, 1 plus the rate raised to the time. That's a future value interest factor. If you subtract 1 and divide by the rate, that gives you a factor you could multiply the payment by to get the future value of the annuity. Again, we will not use that formula, but if you would like to test it, there it is. Just the future value interest factor minus 1 divided by R. Take that factor times the payment will give you the future value of the annuity. So example 6.2 is the future value of an annuity. You deposit $100 per year for 3 years. That is an annuity. A level amount of cash flow, same time period apart, for a fixed or finite period of time. That is an annuity. With the first deposit made 1 year from now, that is at the end of the year, that's what makes it ordinary. The fact that the payments come at the end of each year makes it ordinary. Those payments go into an account earning 7% interest, and the question is, how much will you have in the account after you make the last deposit? Immediately after you make the last deposit. For an ordinary annuity, it ends immediately upon making the last investment or deposit into the account. So we'll be calculating the future value right here, exactly when that third and final payment is made. It's often helpful to draw a cash flow timeline horizontally like this, especially when we're trying to discount or compound cash flows to see what the total value is for an investment, because it helps you to visualize the number of periods involved during which each payment will earn interest. So for this investment, it starts today, but you don't deposit anything today because it's an ordinary annuity. 1 year from now, you'll make the first $100 deposit. 2 years from now, you'll make the second deposit, and then when the annuity ends, 3 years from now, you'll be making the third and final $100 deposit, and that's the point as of which we will be calculating the future value. So ask yourself, how many periods or years will this first payment get to earn interest? Well, since I make it 1 year from today, and the investment ends 3 years from today, this first payment earns interest for 2 years. This one earns interest for 1 year, and the third deposit earns no interest at all because the investment ends at that time. Now we're supposed to compound these payments forward at 7%. So this first payment of $100 would earn 7% interest for 2 years, and it individually will be worth $114.49. Second payment earns 7% interest for 1 year, grows into $107, and then the third payment earns interest for no periods at all, no time. Anything to the 0th power is 1, so that payment is just worth its $100 amount because the annuity ends at that point in time. So the total sum of all those future values is $321.49. That is how much you will have 3 years from today if you put $100 into the investment at the end of each year for the next 3 years and earn 7% on those payments. Now let's use the financial calculator to calculate that. Again, in Chapter 5, we checked to make sure we were in end mode, which is the normal setting for your calculator. It should not say begin, so if it does, you can review page 55 in the course notes or go back to our Chapter 5 calculator setup, and we were able to get rid of that BGN setting, which will be the normal end mode for the calculator. For any time value of money problem, we start using second clear TVM to clear the third row keys on the calculator. The example here has the keys in the same order that your calculator does. You're making 3 annual payments. So N is 3, and you understand it's years that you're going to pay at the end of each year, so it's nice to make a note to yourself that this is an annual annuity. So 3 is the number of years. You're going to earn 7% per year, so IY will be 7. Nothing happens today. You don't put anything in the account today, so there is no present value. The payment key is what we use for an annuity payment where it's the same amount of cash flow repeatedly as long as it occurs the same time period apart. That's what the payment key is used for. So we have a $100 payment amount. Now I made it negative for the calculator here because we will be paying that out. And when we calculate the future value, just like Chapter 5, this will be a positive amount. Because if I'm paying something into the investment, the negative payment amount is an outflow from me paying cash into the investment, then the calculator will tell me the future value is positive, that I will be getting that future value when the annuity is over. So clear the calculator, enter the value 3 first, then press N, enter 7 for the 7%, then press IY, 100, negative using the sign change key, payment, and then compute, and then press future value. As a reminder, just to illustrate the keystrokes here, second, clear TVM, 3N, 7 IY. There is no present value, so it does not hurt anything to put a 0 in there as a double check. 100, negative, payment. Felt good to press that payment key finally, didn't it? So now we've used all those keys for once. And then compute future value, 321.49, and there's our asterisk. That tells us that we computed that amount, and it is that result consistent with what we put into the time value of money keys. Now that was an ordinary annuity. That's what the calculator default is set to calculate, is an ordinary annuity where there's no payment up front and the payments come at the end. So it knew to compound those the appropriate number of periods. Now let's use the calculator to calculate an annuity payment amount. in order to accumulate $100,000 in the kids' college fund, well, that's going to be a future value, right? We're going to accumulate that at some point in the future by age 18. What is the annual payment? We're solving for the payment amount that must be invested if your investment yields 8% per year. Start on the child's first birthday. That simply means you don't invest on the day the child is born. That would be at the beginning of the year. You invest on the child's first birthday. That's the end of the first year. So this is an ordinary annuity. So now you're probably familiar enough that you know N is going to be 18, IY will be 8, and the future value will be $100,000. We'll compute the payment amount. Now, here is a case where we need to understand the consistency between N, IY, and payment. I'm going to compute a payment amount here. The calculator will give me some number for the payment amount. I have to understand whether it is telling me that's how much I will have to pay each year, each month, each day, or what. So I have to understand the frequency involved here, how often the payments are to be made. The calculator does not have a setting for monthly payment, quarterly payment, annual payment. It simply knows how many payments will be made and what rate will be earned per period. You have to be aware that you're dealing with years. That is why I encourage you to write down the periods involved. So you're going to put in 18N, you know it's years. You're going to put in 8 for 8%, 8 IY, you know it's 8% per year. The calculator just knows it's 8% per period, and there will be 18 payments made. You have to understand that this is an annual number of periods and an annual interest rate, and that's the calculator will give you a payment amount. You have to understand it's the payment per year because you put in years for N and IY. So go ahead and clear your calculator, second clear TVM, enter 18N, 8 IY, 100,000 future value, and the computed payment amount will be $26.70 and 21 cents. Now the calculator will put a minus sign in front of that telling you you'll be paying out the $26.70.21 in order to have a positive get $100,000 when a kid is ready to go to college at age 18. So that minus sign the calculator gives you simply means you'll be paying that amount out each year. But certainly it's a positive number of dollars. The minus sign just means it's something you'll pay out. If you had put a minus sign in front of the 100,000, this would be positive from the calculator. So it's just changing the signs, telling you if you want to get cash in the future, you got to pay it out along the way. You have to invest it. Your banker or your 529 college savings fund would look at this just the opposite. They would see this as negative, something they have to pay to you, and they would perceive this as positive, something they receive from you each year for the next 18 years. Here's a question to think about. What if this college fund was established with monthly payments? So instead of making an annual payment of $26.70.21, what if you made a payment at the end of each month, starting when the child turns 1 month old? You make the first monthly payment, and then another payment when the child is 2 months old, etc. If you were to make those monthly payments, would the monthly payment simply equal the annual payment divided by 12, or would it be something else? Well, let's just calculate it and see what we come up with. I'll let the calculator do most of the work here. Here are the inputs that I'm going to ultimately put in the calculator, but let's think about how I would get those. I know I'm going to invest for 18 years until the child goes to college. Now let's not forget second clear TVM before we do anything on the calculator. So the child is going to go to college in 18 years. But I'm going to invest monthly, so there are 12 months per year, so I'll multiply 18 by 12, and I'll see that there are 216 months in 18 years' time. So 216 is going to be my N. That's the number of payments I'm going to make if I invest monthly. Now, again, I know it's months. The calculator just knows there are 216 payments. I need to make a note to myself that those are monthly payments. The college fund earns 8% interest That's an annual percentage rate, or APR. But now that I'm going to be making monthly payments, I'll be earning interest on a monthly basis. So I need to calculate my monthly interest rate. I'll take my 8% APR and divide it by 12, and I'll see that I'm going to earn 2/3 of 1% per month, 0.66666 repeating percent per month, 2/3 of 1% per month. That is my IY. So that's how I let the calculator do the work. Take the 8, divide 12, get my monthly interest rate, and then press IY. I don't have to write it down and re-enter it. I have it on the display. I can just hit the IY key there. I wanted to accumulate $100,000 at the end of the investment. I don't put anything in it today. I didn't start it with an initial deposit of $100 or $1,000 or anything like that. I set it up today. I don't put anything in it today, and then I start making the monthly annuity payments at the end of each month. So I'll compute the payment amount, and I get $208.30, $208.30. Again, the minus sign means I'll pay this out each month, because remember, recall that future value, I put it in as a positive 100,000. So my computed payment will have a minus sign in front of it. I have to pay out $208.30 each month for the next 216 months, or over the course of 18 years on a monthly basis. So that $208.30 with a minus sign in front of it means I pay that out. Now, that $2670.21 was our annual payment. If I just divided that by 12, I would kind of have the idea that I would have to invest $222 each month over the next 18 years. I don't have to invest that much each month if I invest on a monthly basis, though. This computed monthly payment is less than 1/12 the annual payment. Why would that be the case? Well, because if I invest on a monthly basis, then I'm putting money into that account sooner than I would have if I invest on an annual basis, being that it's an ordinary annuity with the payments being made at the end of each period. So for an annual annuity, there's nothing in that account until the end of a full year. If I make the payments on a monthly basis, 1 month after the child is born, I put $208.30 in there. It earns interest for 11 months before I would have ever made the first annual deposit. After 2 months, I put another deposit in there. It earns interest for 10 months before the first annual payment would have even been made. So by investing sooner, I have more time to earn interest. I have more chance to compound and earn interest on interest, and so interest is going to pay a lot more of the college fund this way if I invest on a monthly basis instead of waiting until the end of each year to invest on an annual basis. For curiosity's sake, let's see how much less we will have to invest if we invest on the monthly basis as opposed to making those annual deposits. Annually, we were going to make payments of $2670.21, and we would do that 18 times at the end of each year till the child turns 18. That's the total we would pay into the investment if we invested on an annual basis. Let me save that. I'll show you how to use the memory here. I want to store it into memory. I'll store that into the first memory by pressing Store 1. That puts it into the first memory. I can clear the display without clearing the memory. I can recall 1, and I can get the total of our annual payments back. So this clears the display, not the memory. Now, if I made the $208.30 monthly payments, and I did that 216 times, I would invest a total of $44,992.80. Let me store that in the second memory and clear my display. So what was the total if I invest on an annual basis? Let me recall that from the first memory. That's the total if I invest on an annual basis. Let me subtract how much I would pay in if I invest on a monthly basis. That's what I put in the second memory, recall 2. And the difference there is $3,071. I would invest over $3,000 fewer dollars into the college fund if I just made my investments on a monthly basis. So that's why financial planners always encourage us to invest, start saving early. The earlier you'll invest, the more time to earn interest, the more work your money will do for you. In this case, we could about write a book here on how to save $3,000 on your child's college education, and the only thing the book would have to say is to invest monthly instead of annually. So you can save quite a bit by making those monthly payments instead of waiting until the end of each year, because interest is going to do so much more to help pay for college that way. Now let's look at the present value of an annuity. The present value of an annuity is the sum of the individual cash flows. So cash flows are additive whether we're talking about future values or present values. We're going to use a 10% discount rate initially. So this investment here is going to provide $100 to be received at the end of each year for the next 3 years. And we want to know what that investment is worth if the appropriate discount rate is 10%. Well, with present values being additive, we just sum up the three individual present values. You're going to get $100 1 year from now. We'll discount it at 10% for 1 year. You'll get another $100 2 years from now. We'll discount it 2 years at 10%. And then the third payment is 3 years from now, discounted 3 years at 10%. So those individual present values are shown, and the annuity is equal to the sum of those three present values. So if I'm going to get $100 at the end of each of the next 3 years, and I require a 10% rate of return on my investment, then I could invest $248.68 today, and that would be the same as receiving $100 at the end of each of the next 3 years. Now, when we did our very first example, 6.1, with the irregular cash flows, we verified that the present value was equal to the sum of the future cash flows to be received, as long as we could put this amount on interest and replicate the cash flow stream that we were entitled to receive. So think about this. If I give up the three $100 payments, I should be entitled to get $248.68 today. If I were to invest $248.68 today at 10%, I should be able to generate those three $100 payments myself. Remember the idea of indifference. I'm indifferent between $248.68 today and $100 at each of the next 3 years, as long as I can turn one into the other. So let's see if we can replicate this. If I had the $248.68 today, and I earn 10% interest on that investment, then it's going to grow by 10%. So this is today, and then in 1 year, I would have 10% more money. So the $248.68 growing at 10% would be worth $273.55 1 year from now. I was entitled to a $100 payment 1 year from now, so I'll pull that out, and that will leave me $173.55. I'll invest that at 10%. That was my discount rate, so I should also be able to compound at that rate. So in 2 years' time, the $173.55 will grow for 1 year at that 10% rate. So 2 years from now, I'll have $190.91, at which time I will take out my second $100 payment, and that will leave me $90.91. In 3 years, I will have been able to invest over the course of that third year. I'll have my $90.91 at the end of year 2. It will grow at 10% over year 3. So at the end of the third year, I will have $100. I can take out my third and final $100 payment, and there'll be nothing left. So what I was able to do is take the $248.68 today, and it will, earning the 10% interest, allow me to take the payment out at the end of the first year. It continues to earn 10% interest. What's left over earns 10% interest. I pull out the second payment 2 years from now. The balance then earns 10% interest and allows me to pull out the third and final payment with nothing left. So that's that idea of indifference. I'm indifferent between the $248.68 today or $100 at the end of each of the next 3 years, because I can turn one amount into the other just by investing at that 10% discount rate. Notice, if you look at those cash flows, how the present value of each of them individually becomes smaller and smaller the farther into the future those payments are to be received. So each one of the payments is $100. The first one comes 1 year from now. It by itself is worth $90.91. The second payment comes 2 years into the future. Discounted at 10%, that payment by itself is worth $82.64, and the third one is worth $75.13. So you see how the present value of each payment individually is getting smaller and smaller the farther into the future it is to be received. So we know the longer we have to wait to receive the same number of dollars, the less it's worth because of the time value of money. So we know, again, present values are additive. The present value of the annuity equals the sum of the present values of each of the payments in the annuity stream. We just added up their present values, and that gave us the present value of the annuity. This present value interest factor of an annuity you can calculate, and that is our future value interest factor there. Its inverse is the present value interest factor. So 1 minus the present value interest factor divided by R is the present value interest factor of an annuity. Take that factor, multiply by the payment amount, and that will give you the present value of your annuity. We will not work with the formula. You can verify that on your own. We will use the financial calculator. But again, you would just take the payment times that factor to get the present value of the annuity. In example 6.5a here, we're going to look at the present value of an ordinary annuity. It's going to provide $1,000 at the end of each of the next 5 years, and we're going to discount those cash flows at 7%. Again, a timeline is always helpful because it helps us see the proper number of periods to discount or compound, whichever way we're working. It's not real hard for the annuity, because the ordinary annuity, because the first payment is discounted 1 period, the second payment is discounted 2, and so on. So the present value of the annuity was simply the sum of the present values of all the individual annuity payments. So this annuity is worth $4,100.20 when you discount at 7% per year and add up the present values of all the annuity payments. Now the calculator solution should be fairly straightforward. We know we're going to receive $1,000 at the end of each of the next 5 years. So we have a $1,000 payment amount. The 5 is the number of payments, and we make a note that it's years, they're annual payments. The 7% discount rate is the IY, and we make a note that it's per year. And also remember, this payment is per year. So everything is on an annual basis. 5 years is 5N, 7% per year is 7IY, 1,000 is the payment we're entitled to receive, so 1,000 payment is the annual payment. So I compute the present value, and I get the present value of the ordinary annuity, which is $4,100.20. And the calculator will put a minus sign on that present value because we made the payment amount positive. If I want to receive $1,000 per year, I would have to invest, so there's a minus present value, I would have to invest $4,100.20 today to be able to get $1,000 at the end of each of the next 5 years. Now, if those payments were in annuity due form, where the payments were to be received at the beginning of each year, we can just make a simple adjustment. Since the payments come up front, I do make the first payment today, and I make the payment at the beginning of each year for the next 4 years. So today plus at the beginning of each of the first, second, third, and fourth years. By making those payments up front, then each one of those payments has a chance to earn interest sooner because they're made at the beginning of each year, not the end of each year like an ordinary annuity. For present value purposes, I will be discounting each payment one period less. We'll illustrate that with a timeline and it should make sense, but initially let's just think about it. If I make the payments at the beginning of each year, then I'll discount them one period less. Each payment will be worth 7% more. So the total of the entire annuity will be worth 7% more, $43.8721. I took the present value of the ordinary annuity and increased it by 7%, and I got the present value of the annuity due is $43.8721. So let's check it out and see if that does turn out to be the case. Here is the annuity as if it were an annuity due, where you do make the first $1,000 deposit today, and you make one at the end of each year for 4 years. Well, that is really the 5-year ordinary annuity with each payment just slid 1 year closer to us. So the 5-year ordinary annuity had a $1,000 payment here and had 0 here. So what we've done is we've slid each payment 1 year closer to us. So each payment now gets discounted 1 year less. No periods discounted for the first one. 1 period, 2, 3, 4. So the total present value of this annuity due is the $43.8721. Discount the first payment, no time at all. Anything to the 0th power is 1. It doesn't get discounted at all because it occurs today. It's already a present value, so it's still worth $1,000. The first payment now gets, the second payment now gets discounted only 1 year because it comes at the beginning of the second year, which is only 1 year from now. So with the payments made at the beginning of each year, they're discounted 1 year less than they were before. They're worth 1 year more interest. So this annuity due result is 7% greater than the ordinary annuity because every payment got discounted 1 year less. You can look at your discounting and each one of those is 1 year less than it was for the ordinary annuity result. So again, we took the present value of that ordinary annuity, $4,100.20, multiplied by 1 plus the 7% interest rate because we discount 1 year less, and that is the present value of the annuity due. If we were calculating a future value, it's done the same way. We just take the ordinary result and we add 1 year more interest. You might feel like you would, for present value and future value, you would approach this differently somehow, but whatever the ordinary result is, the due result is worth 1 period more interest, whether it's a present value or a future value, because the annuity due has the cash flows occurring sooner. So for a present value, they're discounted less. They're worth 1 period more interest for the annuity due. Take the ordinary result and add 1 period of interest to the entire present value, and you'll get the present value of the annuity due. For the future value, for the annuity due, your payments come sooner, so they compound more. So take the ordinary result and then compound everything 1 more period. Add 1 period worth of interest, and you'll see that the future value of the annuity due is larger by 1 period worth of interest. The present value of the annuity due is larger by 1 period more interest because you discount 1 period less here and you compound 1 period more here. That's the same thing. The annuity due is worth 1 period more interest. Now let's solve for an annuity payment amount. This is a handy thing to be able to do if you're going to buy a house or buy a car. And I hypothesize that if you just carry your financial calculator into the car dealer, they'll shave off a few $100 because they'll know you know what you're doing. So try that sometime and see if it might help. What we're doing with annuity payments is we're establishing a series of payments that will exactly equal the present value of the amount you borrow. In example 6.6, we're going to calculate the monthly payment on a $100,000 loan. This will have monthly payments over the next 30 years. A 30-year mortgage is typical. 15-year mortgages are typical as well. In this case, we're going to repay the loan over 30 years on a monthly basis at a 9% quoted interest rate. Now that 9% is not really what we're going to use in the problem because we're going to repay on a monthly basis. We need to convert that to the appropriate monthly interest rate. This 9% APR has to be quoted to us by law, but then we're just going to turn it into the monthly rate so we can use it to calculate the monthly payment. Here are the calculator inputs, but let's think about how we would get those, letting the calculator do most of the work for us. Clear the display. I know I'm going to repay over 30 years, so I've got a 30-year mortgage, but I'm going to pay on a monthly basis, so I'll multiply that by 12 months per year, and it gives me 360 months or 360 payments that I'll make on a monthly basis. I'm not sure that I cleared TVM, so let me press second, clear TVM, and that sets everything on the third row to 0. Now that I know there are 360 months, I'll press N because I'm going to make 360 payments. The 9% quoted interest rate is for a year. That's an APR. Let me take the 9% and divide it by 12 to get a monthly rate of 0.75 or 3/4 of 1% per month. So with 0.75 on the display now, I'll press IY and my interest rate is 0.75% per period. Now, remember, clear the display here. Let me recall N for a minute. The calculator knows I'm going to make 360 payments. I know they are monthly payments that I'm going to make, because I know I'm working in months, so I need to write down months, so I'll remember that. The calculator only knows I'll be making 360 payments. I know they're monthly payments. Recall the IY. The calculator understands it's 3/4% per month of interest that's going to be charged on this loan. I know it's a monthly rate, so I make a note that it's 0.75% per month. I borrow $100,000 today. That's my present value. I put it in as positive because I get the $100,000 from the lender today. I want to know what the payment is. As a double check, there's nothing that happens at a single point in time in the future. There's no single lump sum future value, so I'll put in a 0 FV there. When I cleared the third row, it became a 0 anyway, but that's a nice double check. So let me compute my payment, and the calculator tells me it's $804.62. 804.62 with a minus sign in front of it, meaning that I will pay that out. The calculator doesn't know if it's telling me that I'll pay this annually or monthly or quarterly or what. I know it's monthly because I put in a monthly number of periods and a monthly interest rate. Then the computed payment will be the amount I'll pay per month, $804.62. So I know it's monthly. The minus sign the calculator put in front of it means I will pay that out each month, because the present value I put in is positive because I get the $100,000 today when I make the loan. I repay, so the minus sign means I repay that amount each month. My banker would look at a minus sign here because they pay out the $100,000 today, and they would look at a plus sign here because they'll get those monthly payments. So we're just on different sides of the table, and that's all the plus and minus signs mean to the calculator. It's which way the cash flows. Now let's look at how long it takes to repay a loan. In this case, I borrow $100,000 at 10% interest, and then I just made up a nice, neat annual payment of $12,000 per year to illustrate what happens, and then later we'll convert that to a monthly payment to compare. So how long will you pay $12,000 per year in order to pay off a $100,000 loan if you're charged 10%? Well, in this case, everything is annual. I put in the annual interest rate of 10%. I put in the $12,000 annual payment. So when I compute N, I will be calculating the number of annual payments I'll make. In other words, N is going to be the number of payments. I know it's a payment per year because I put in the rate per year and the amount I'm going to pay each year. So the computed N is the number of annual payments I will make, which is 18.8. Now, I either make 18 payments or I make 19 payments. I can't write 18.8 checks. I either write 18 checks or 19 checks. So in this case, 18.8 means that I will make 19 payments and the last one will just be smaller than the others. So to fully pay the loan off, the last payment will not need to fully be $12,000. I did not get an integer number of payments, so the last one will be less than full $12,000. $12,000 will not be needed to pay the loan off at the time I'm making that last payment. Now let's take our $100,000 loan and see what happens if we pay it back on a monthly basis. Let's take our $12,000 annual payment we were making and divide it by 12 to get a $1,000 monthly payment. What we'll see here is we're going to pay the loan off faster because instead of waiting till the end of the first year to pay $12,000, I wait 1 month to pay $1,000, and then 2 months from now I'll pay another $1,000, and so I pay the loan back more quickly this way because I reduce what I owe faster by making payments on a monthly basis. The monthly payments cover the interest for that month and then have a portion of the payment to reduce principal, so I lower what I owe, so it lowers the amount of interest I'm charged and it pays the loan off faster. So here's what it would look like on a monthly basis. I would take the 10% rate that I was quoted and divide it by the 12 months per year to get a monthly rate of 0.8333% repeating, and that's my IY. I borrow $100,000 up front, so $100,000 is that positive present value. I'm going to repay $1,000 on a monthly basis. Now it's important to make sure the signs tell the story in an instance like this. I get $100,000 up front, I pay $1,000 monthly. Something has to be positive and something has to be negative when I'm calculating the number of periods or the interest rate. If all the cash flows are positive or all the cash flows are negative, the calculator does not understand what you're asking it. So some cash flow has to be positive and some has to be negative when you're computing the number of periods or the rate per period. There's nothing that happens one time in the future. There's no lump sum future value, so it's 0 FV, and then I'll compute N, and I get 216. Now, I know the 216 is months because I put in an interest rate per month and a payment per month. The calculator tells me I make 216 payments. I understand those are monthly payments. If I wanted it on an annual basis, then I would take the number of monthly payments and divide by 12 and see that I would pay the loan off in 18 years' time. It was 18.8 years when I paid $12,000 per year. $1,000 per month pays it off almost a year sooner, 8/10 of a year sooner. I don't have to make that 19th payment. I make 216 monthly payments and the loan is paid off. That's because the monthly payments pay the loan down sooner, so the amount of interest charged on the loan is less because my loan balance is being reduced more quickly with the monthly payments as opposed to by making annual payments. Now, let's talk about perpetuities. A perpetuity is a perpetual annuity. An annuity had 3 things. A perpetuity has 3 things. The only difference is, with the perpetuity, the cash flows go on forever. Similar to an annuity, there's the same amount of cash flow, and it occurs the same time period apart. But an annuity had a finite or fixed number of periods. The perpetuity goes on forever. There's no end to the cash flows or the payments made under a perpetuity. An example of a perpetuity, in theory anyway, is a share of preferred stock. Preferred stock offers some stated dividend and it has no maturity. The dividends occur the same time period apart. So the preferred stock, in theory, will pay you the same amount of cash flow the same time period apart forever. That is our definition of a perpetuity. Perpetuity is easy to value. The present value of a perpetuity is simply the payment amount divided by the discount rate. For example, if a perpetuity offers you $100 to be received each year forever, and you require a 10% rate of return on the perpetuity, then what's the present value of that perpetuity? How much would you be willing to pay for an investment that gives you $100 at the end of each year if you require a 10% rate of return on your investment? Well, the perpetuity formula says the present value is that payment amount divided by the discount rate. The payment's $100 per year. You discount those payments each at 10% annual rate, add up all their present values, and you would get a $1,000 value. Now obviously we can't draw the timeline for the perpetuity because it would go on forever, but you can envision getting $100 1 year from now, 2 years from now, 3 years from now, and discounting all those cash flows at 10% for the appropriate number of years and adding them up. Well, that's what we're doing when we use this formula. Now, that should make sense that I would be willing to pay $1,000 for this investment if I require a 10% return on my investment. Because if I pay $1,000 up front, 1 year from now I get the first $100 payment. That does give me my 10% return for the first year. Because I pay $1,000 today, 1 year from now I get $100, that's a 10% return for the first year. 2 years from now I get another $100 payment. That's my 10% return for the second year. Every year I get $100, that's a 10% return for that year. So another way to think about the perpetuity is we're just creaming the interest off the top. I invest $1,000, it earns 10% for me, that gives me my $100 payment at the end of each year. So every year my $1,000 is earning me 10% when I receive the $100 payment for that year. The return on a perpetuity is simple as well. It's simply the payment divided by the present value of the perpetuity. In this example, 6.8 Part B, I am told that I pay $2,000 for the perpetuity and it gives me a $100 annual cash flow. What kind of return am I earning on my $2,000 investment if I get $100 per year? Well, I take the $100 payment, divide by the $2,000 I invested, and that gives me a 5% return for every year. Because each year I get $100. I invested $2,000 up front, so I'm getting a 5% return for each year. If the payment amount is constant, and it certainly does not change, if the 5% rate continues to stay the same, then my perpetuity will always be worth $2,000, so I could sell it at any time in the future for $2,000 as long as the 5% return is holding constant. I'm going to get $100 per year. If we value it using a 5% rate of return, it would be worth $2,000 at any point in time. Because to value it, you would take the $100 payment, divide by the 0.05, and that would give you that $2,000 value. So if the rate and the payment all stay the same, the perpetuity's value will never change either.